Have you ever stopped to think about the hidden arteries of our buildings? No, not the plumbing. I'm talking about the main power cables. Today, we are going to pull back the curtain on the critical engineering that keeps our lights on and, way more importantly, keeps us all safe.
Right? It's a great question, and the answer, well, it's a fascinating and really delicate balancing act. You see, getting it right is the difference between a system that runs smoothly for decades and, a total catastrophic failure. So let's dive into the real science behind professional cable design.
I mean, just think about it for a second. These main cables are the unseen lifelines, the absolute core infrastructure that delivers power from the grid to every single thing you plug in. Designing them properly isn't just a good idea, it's the absolute foundation of a safe, dependable building.
And that right there is the heart of the challenge. You can't just go out and pick the thickest, beefiest cable you can find. An engineer has to juggle a whole bunch of competing factors, things like cost, the physical space you're working in, and of course safety, to land on the one, single, perfect solution for that specific job.
So, how do they actually solve this puzzle? Well, it all boils down to 4 fundamental pillars of design. You can think of these as the non-negotiable checklist that every single electrical engineer has to master to get this right.
All right, here they are. You've got current carrying capacity, voltage drop, fault withstand, and disconnection time. Each one of these asks a really critical question about how that cable is going to perform, not just in its day-to-day life, but in a worst-case emergency. Let's dig into the first 2.
Okay, so first up, we have the 2 criteria that engineers deal with constantly: making sure the cable can handle the electrical current and making sure enough voltage actually makes it to the other end. Now, both are absolutely essential, but you might be surprised to find out which one usually ends up being the deciding factor in most buildings.
Current capacity. It's all about heat. As electricity flows through a wire, it naturally warms up. The capacity is simply the absolute maximum current that cable can handle before its insulation gets dangerously hot and starts to break down. For modern insulation, like something called XLPE, that limit is usually around 90 degrees Celsius. This is where we start the design, but interestingly, it's almost never the final answer.
Now, voltage drop, that's a whole different beast. The best way to think about it is like water pressure in a really, really long garden hose. The further you get from the tap, the weaker the spray gets, right? Electricity is exactly the same. If the voltage drops too much by the time it gets to, say, a motor or a computer, that piece of equipment might flicker, run poorly, or just not turn on at all.
And here it is, the key insight. In the vast majority of real-world building projects, especially when you have long cable runs, it's not the current it can handle, but the voltage drop that forces the engineer to pick a bigger, thicker cable. The cable might be perfectly fine with the heat from the current, but it has to be upsized just to make sure the voltage stays high enough at the destination. Okay, now check this out, because this is where things get really weird and counterintuitive. For a smaller cable, a poor power factor, that's the 0.8 or 0.6 you see there, actually improves the voltage drop situation. I know, it sounds crazy. But now look at that massive 240 millimeter squared cable. The voltage drop gets way worse. So what's going on? Well, in big cables, another property called reactance becomes the dominant player, and it completely flips the script on what you'd expect. All right, so we've sized our cable for normal everyday operation. But what happens when things go really, really wrong? Now we have to shift gears and plan for the absolute worst-case scenario, a massive electrical fault.
No, that is not a typo. During a short-circuit fault, say right near a big building transformer, the current can spike instantaneously to 25,000 amps, maybe even more. That is just a mind-boggling amount of energy, and the cable has to somehow survive it for the fraction of a second it takes a circuit breaker to trip.
So what it all comes down to is this: a battle between 2 forces. On one side, you have the destructive energy from the fault, which we call I squared T. Think of it as the explosive burst of heat from that giant current. And on the other side, you have the cable's own built-in strength, its K squared S squared value. The design is only safe if the cable's strength is greater than the fault's destructive energy. It's a simple and pretty brutal equation for survival.
So once we have all the electrical math locked in, we can start looking at the physical cable itself, because the choice of what it's made of, the conductor and the insulation, has a huge impact on performance, cost, and of course, safety. When it comes to the conductor, the big choice is usually between copper and aluminum. Now, copper is the better electrical conductor, hands down. That means you can use a smaller, thinner cable to do the same job. But, and this is a big but, Aluminum is way lighter and a whole lot cheaper. So engineers are always doing this trade-off. Do you want better performance and a smaller size, or a lower cost and an easier installation?
And the insulation is just as critical, especially when you start thinking about fire safety. Older PVC insulation, it works fine electrically, but in a fire, it gives off this thick, black, toxic smoke. That's why modern buildings almost exclusively use LSF, which stands for low smoke and fume, and that XLPE insulation we mentioned earlier. It can handle higher temperatures, and crucially, it is much, much safer in a fire. It's the standard for a very good reason.
So how do you keep track of all this stuff? Well, you get these standardized codes. This is a European harmonized code, and it might look like a bunch of random letters and numbers, but it's basically a recipe card. The H tells you it's a harmonized standard. 07 tells you its voltage rating. R, N, and F tell you all about the insulation, the outer jacket, and whether the conductor is flexible. It's a universal language, so engineers anywhere can specify exactly the cable they need.
Okay, so let's tie all of this together. What is the final blueprint? What does it take to design a main power cable that is truly safe, efficient, and reliable for the long haul?
First, remember that design is a multi-step process. It's not just plugging one number into one formula. Second, more often than not, voltage drop is the real kingmaker, the thing that decides your cable size, not current capacity. Third, and this is huge, planning for those insane fault conditions is absolutely non-negotiable for safety. Fourth, the materials you choose are a critical balancing act. And finally, even though we use powerful software these days, nothing replaces the judgment of an experienced engineer to make sure the design is truly safe.
It's really a testament to incredible engineering that we never, ever have to think about this stuff. But behind that simple, boring light switch is a whole world of careful calculations, critical decisions, and trade-offs, all working together perfectly to keep the lights on and keep us safe. Pretty cool, huh?